Hi everybody, Dr. Pingle here. We're beginning a series of lectures on Lidar. Today is part one, definitions, data sources, and visualization. So many of you have probably heard of Lidar before. This is getting to be a fairly common technology. Hopefully you've been exposed to this in your GIS classes so far. You may not have worked much with the data, and that's kind of what these next couple of lectures are about. But it's a very powerful technology, one of the big innovations, I think, in geospatial data in the last 20 years. It's been around a little bit before that. I would say it really got popular about 10 years ago, from about 2010 onward or so, when a lot of the counties in the United States started scanning and putting a lot of their data up online. Lidar itself is sometimes thought to be an acronym, light detection and ranging. Some of the old hands in the industry will tell you that that's not actually true. That it's a portmanteau of light plus radar. The truth of it doesn't really matter so much anymore, but you might want to keep that in mind as sort of an interesting story. It's sometimes abbreviated all in caps like LIDAR, L-I-D-A-R. Occasionally the I is lowercase. Increasingly, LIDAR is just written as a single lowercase word, which is actually my preferred way of writing that. If you look at radar, radio detection and ranging, you don't really ever see it with the A lowercase. You don't really see it all caps anymore. Radar is usually just written out as a single lowercase word. So I'm a big advocate of making that happen for the LIDAR community as well. Sometimes this is referred to under a couple of other names. Laser scanning is a popular way of saying it. When you talk about the instrument that it's mounted on, sometimes these will be referred to as airborne laser scanning, terrestrial laser scanning, mobile laser scanning. So lots of different sort of words can come before the laser scanning, but oftentimes the data, especially that you're likely to be working with, is going to be gathered from an aircraft. Usually this is a fixed wing airplane, although sometimes it's mounted on a helicopter. And essentially what you've got here is an instrument that emits lasers, pulses of light, usually in the near infrared spectrum. They bounce back from an object. The sensor collects how long it took for that bounce to occur. It keeps track very carefully of the direction that pulse was sent out. It's got the instrument itself is fitted with inertial sensors, so it knows the tilt in 3 axes perfectly. It has an onboard GPS, so it knows precisely where the instrument was. And so with a combination of this, essentially, with the time delay, it can figure out the distance from the sensor, and with all of those pieces of information, it can figure out exactly where where the reflecting object was. This happens hundreds of times, thousands of times, hundreds of thousands of times per second, depending on the instrument. And the result of that is essentially what's called a point cloud. So each single return from the instrument is a single point. But if that happens lots and lots of times over the course of maybe several hours that it takes to scan an area, you wind up with millions, potentially billions of points, depending on the resolution of the scanner. This is kind of a classic example of what that looks like. This is an image of a colorized point cloud representing a bridge. You can sort of make out the factory in the background. You can make out the coastal terrain. The coloring is a little bit unclear. We'll talk a little bit about how these things are rendered here in a minute. But you can certainly make out features and shapes and see what things are. This is an example of a LIDAR point cloud downloaded from VGen, one of the Virginia distributors of geospatial data. So I've downloaded a tile and actually fused a couple of the tiles together and visualized it in a program called Cloud Compare and exported it to an animation. The symbolization here is color mapped to height. So you can visualize point clouds in a number of different ways, and we'll talk about those. Here we've got red standing in for a high elevation area, green kind of a mid elevation, and then blue a lower elevation. Like all kinds of other hypsometric tinting, you have to be careful not to assume that what you're looking at is land cover. So blue likes to kind of evoke water. That's clearly not the case here. You can probably make out several features, and I would encourage you to try to do that as you're watching this. The drill field is pretty easy to spot in the middle, and you can probably spot some other features in here. This is an example of a kind of a common LiDAR view. Zooming in on this a little bit, this is a small extract of that. This is an area northeast of the drill field. You can spot the power plant there, and you can probably spot a couple of other things here. This is kind of the area where some of the cadets practice. This is where the old geography building at Major Williams was. And once you zoom in a little bit, you start to really kind of see the point-based nature of this data set. We're going to zoom in here just to even a little bit further. But you should start seeing sort of the, what you're looking at is they're not solid surfaces. You're looking at sort of disconnected points in space. Where the scan is fairly dense, it looks almost flat. So some of these kind of lawn areas look pretty flat. Building rooftops come in at pretty high resolution, but the trees are fairly spotty. And certainly the building facades are spotty, and we'll zoom in on that here in a second. So what should we notice about that point cloud? We've got a couple of buildings here extracted, or actually this might be a single building from two different views. What do you see? One thing you should see is that the tops of the buildings are much better defined than the rest of it. At this kind of zoom, you really can see the separate points in space. The reason for this appearance is how the data was collected. So most of the LiDAR is collected via aircraft. They fly at a fairly high altitude. The higher they fly, the more they can scan, the more quickly they can scan effectively. They have a bigger footprint on the ground that they can scan. They can fly further apart. And so it speeds up the data acquisition process. But when they fly at those altitudes, the LiDAR essentially doesn't see it sort of looking downward or more or less downward all the time. And so it doesn't image the sides of buildings all that well. Another thing you might notice is that the trees show up as, I wouldn't say complete, but sort of you can really make out the shape of trees. What's happening here is LiDAR can actually penetrate through a little bit of vegetation. And so when it hits the tree branches, actually some of that beam makes it through and can collect in multiple spots. So LiDAR has multiple returns. Oftentimes in the data products you're going to be working with, you're only going to get things with one or two or three returns. But depending on the altitude of the aircraft, depending on the sensor, you can get a lot more returns than that. But in this case, you can really kind of see both the ground and the trees. Because the laser can penetrate. Hard surfaces, though, if you kind of look at the lower right, you can really start to see areas where there aren't any points. This is essentially where the opaque rooftop prevents imaging anywhere below it. So there are limitations. Obviously, you can't see through buildings. If there are overhangs, if the data was collected at kind of an angle, things can essentially cast shadows into the data. And so you do have to be a little bit mindful of those limitations. It's a much better data product of capturing the full 3D structure than, say, like DEM. But on the other hand, it's not perfect. You're still going to miss a lot of the things that you might be used to seeing, and the sides of buildings and the ground below them is particularly obvious. The point cloud itself, the data it's essentially tabular data. Imagine this like a big spreadsheet. Each observation is a row, and you have a couple of different columns of information. The most useful columns of information in that data set or attributes are the spatial data in X, Y, and Z coordinates. Most of the time, those X, Y, and Z coordinates are going to come to you referenced in a fairly local coordinate system. In the United States, most of the time, these are going to be in state plane coordinate system. If you're abroad, they might be in UTM. So you're going to get things that are essentially in meters or sometimes in feet, depending on how they were collected. And most of the time, when the people who gather this data turn it back over to the stakeholders, they'll provide it in both UTM and state plane these days. Although conversion between the two is actually lossless since it's point data. So XYZ data, you've got the location in space. You also get intensity data. As the laser hits an object, you get information about how essentially the strength of the return. So you shine a light, how much of that light comes back. This reminds us a little bit of the discussion about hill shades and shaded relief and how that stuff works. The amount of light that gets returned is a function of a couple of different things. It's a function of how reflective the object is. So a mirror is going to return more of that light back than a rough surface where the light can get sort of trapped in the cracks and crevices. But it's also a function of the color. So a white surface is going to reflect more back than a black surface. You can actually, we'll look at some visualizations of this, but you can actually kind of map this stuff as if it's sort of a gray tone, black and white television kind of a experience. That's not exactly true because it does vary according to the material. It also varies according to the angle at which it's hit. If you're looking at something, a surface that's not perpendicular to you or to the emitter, then it's going to start to lose some of that intensity. Less of that's going to be reflected back. And again, that's a lot like sort of how the shaded relief system works. The greater the slope, the less the slope, according to the viewer, the less light is going to come back. What's missing from that? You're going to be missing color mainly. So most of the time when you fly these instruments, or at least up until the present, most of the time when you fly these instruments, all you're really getting back is sort of this X, Y, Z and intensity values. There's actually a few other variables that you get back as well. It's actually quite a lot of variables. Most of those are not super useful to most in visualization and processing of the point cloud, although some of them come in handy all the time. And we'll look at those here in a second. But what you're not getting is color. The reason for that is you're really only getting back sort of what the active sensor, the laser, is kind of sending back. That's starting to change. In some cases, in more and more cases, cameras are essentially being paired with these things, and so you're getting color information back at least about what's on the top. So even if you're sort of shining a laser and it gets through the canopy, you can't see underneath, so you can't necessarily color what's underneath. But the pairing of sort of an active laser with a passive camera can make for a pretty well-colored point cloud. You can also apply a color ramp, so you can use symbolization just like any other kind of sort of cartography or geoviz. And then you can also pair, even if your mission didn't include a paired camera with the laser, you can kind of go back and use things like remote sensing products to color those back again. So that's kind of an effective way of attaching attribute information to the LiDAR data. This is an example of sort of illustrating the idea of color mapping in this context. Here we have sort of a section of campus again. Most of that section we're just visualizing in this sort of whitish gray with a little bit of shading applied. But then a section of it we're applying a color map to. So this is just sort of to illustrate the idea that what you're looking at, the color patterns can be manipulated quite easily. This is the same section of campus where the visualization is coded to the intensity value. So the gray tone value that you're seeing here is the intensity value that's coming off of the laser. And you can start to see both differences in, it looks semi-real, but some of the colors or shading is a little bit off. You can see that trees, for instance, are not returning back nearly as much light as sort of the pavement. This is where material matters a good deal. You're not really looking at a black and white image, but it's not so far off that you can't get some good visualization off of just the intensity value. Again, intensity varies according to the properties of the material, the color, the angle that it struck. So you're not looking at a perfect rendering of what's going on here, like your eye would see it if it were in black and white. But all of these sort of properties of the laser and the position and the material all play a part in terms of how the intensity comes back. One other really kind of important bit of information that comes with point cloud is a classification. So the points in space can be assigned an attribute, an integer value that corresponds to sort of a standard set of classification categories. So 2 is ground, 0 is unclassified. Oftentimes we'll mark things as noise, we'll mark things as buildings. How particular you want to get with this depends on the algorithm and your purpose for the data set. But essentially every point gets assigned one of these classification values. By default 0 or unclassified, but as you go back through you can classify this stuff. The classification is derived during post-processing, meaning after the area is flown, it comes back. There's a lot of sort of quality control that's done to sort of check to make sure everything is as it's supposed to be. Things need to be accurately compared to ground measurements. They use what are called ground control points to precisely position the cloud in space, to report error values and things like that. But one of the things that they also do is apply this classification. That's done by algorithm, so humans don't go in and do this. Computers go in and assign these points. Remember, you're looking at tens or hundreds of millions or even billions of points, so there's really not an easy way for people to go in and do this. So computers go in and they make guesses using sophisticated algorithms, and this is kind of an area of active research, writing better and better algorithms to classify these things better and better. Current classifiers are only accurate, even just identifying what's ground and what's not ground is only accurate to about 92–93%. And so there's a lot of opportunity to design better algorithms and better ways of interacting with this stuff to improve that classification code. So you should always take these classifications with a grain of salt. They are never perfect. In some cases, the data acquirer will go in and make some hand corrections. Different software packages make that easier or harder. And so again, sometimes there's some quality control, but with hundreds of millions or billions of points, there's really no way to assure total accuracy on these classification values. So always expect some error with those values. A lot of the data that you're going to download is going to be pre-classified. There are tools that you can use as sort of an end user to go back and reclassify things. Different software packages will let you do this. But again, because these things are done by computer, there's going to be a lot of error. And so these are some examples here. You can kind of look at this. This is a data set visualized in ArcGIS with a box drawn across sort of a transect, and you can start to see where things are color-coded, what's being classified as what, and you can likely pick out some errors here. So if you imagine a Lidar point file as tabular data, essentially, imagine it as a big Excel spreadsheet or something. Each row is a single observation. That row has a number of different columns. The X, the Y, the Z, the intensity, the classification that we mentioned, but it can have a number of different pieces as well. So it can have RGB values associated with it. If it's collected with LiDAR, it's usually going to have things like the number of returns there were, what return number this particular row is, the time at which it was gathered, scan direction, lots of different things that probably you're not likely to use. Using the return number, whether this is the first return or the last return, is often valuable. But many of these things like edge of flight line, probably not likely to be used by most LiDAR consumers. LiDAR data is distributed in a couple of different formats. The most common format still, although it's getting fairly close, is what's called an LAS file. This is a binary file. Those files are sort of like imagine them like shape files. There's a data specification, sort of how they're written to disk. That current spec is at 1.4. There's a version 2.0 of this LAS specification kind of proposed and under consideration right now. So it's a very sort of precise specification for how point cloud data, particularly LiDAR data, I should say, but many sort of geographic point clouds would be written. This is an example of what that looks like. These are Googleable, so feel free to take a look at one of these. This is the last specification, 1.4 revision 13. This is an example of what the header binary looks like. If you're taking the algorithms class, this might make a little sense to you. If you're not, maybe kind of bookmark this in your brain. Maybe you take that later and take a look at it. But essentially, the first several sequences of bytes in this file are what's called a header, and that header describes things about what's contained in there, including things like a bounding box, so the minimum x, minimum y, the offset, sort of a way to write these coordinates in a shorter value. Lots of other, the file creation day and time and year, things like that. So feel free to kind of take a quick look at this and familiarize yourself with some of the metadata that's associated with each LiDAR file that gets distributed. If you're interested, I've written a pure Python LiDAR reader. So this is distributed as part of my lab's package NeilPy that sort of takes apart various kinds of data, including LiDAR data. This will read your LiDAR data into a pandas data frame. So feel free to take a look at this. You may find it interesting. That's a little bit about, we've seen some examples, we've talked about sort of how it's written to disk. We'll talk about a couple of other formats here in just a second. But where do we get the data, where do we get LiDAR data if we wanted to play around with it? There are a number of different sources. We'll take each of these kind of in turn. The national map is probably still your best one-stop shop for this stuff. That's where most of the geographic data that you're going to be using is going to be located, at least, bigger, more national level stuff. So LiDAR data is distributed via the national map. There's also an interagency elevation inventory. This is a nice spot that NOAA had initially managed. I expect at some point this will probably go away. I think it's been a little bit superseded by the national map, but it still has a role to play in this environment. The USGS has partnered with a group that produces sort of a web browsable version of this stuff, where you can actually go and manipulate these things right through the web browser, which is really cool. So that's called Entwine, and I'll show you that interface. The data can be downloaded there. I think it's probably safe to say it's mostly intended for visualization, but you can certainly access the data that way. Many state and sometimes county GIS offices will distribute this via their own website or via a dedicated secondary website. And then I want to show you Open Topography, which is a sort of a user community of point cloud data. Think of it a little bit like OpenStreetMap or Wikipedia. Essentially, the public can interact and both publish and download LiDAR and other point cloud data sets. So before we get into those, let's just mention formats. So I said LAS is the default standard format. Again, it's a binary format. One of the problems with this format is it's actually relatively large. So we said that point clouds can get up tens of millions, hundreds of millions, billions of points. That's a lot of data. And so things recorded in LAS format can get big pretty fast. And so a number of years ago, people started to figure this out and started to look for alternative ways to shrink that file size. One of the things that people actually do is actually just zip these things up. So you can take a LAS file and you can use 7-zip or another zipper and just compress it that way. That's a fine way to store the data. It produces file sizes that are very reasonable, but it's not directly usable. You have to unzip it before you can take a look at it. It's an okay strategy, though. Lots of formats have sort of adopted this, like let zip take care of the compression. I only want to really handle the specification. So not so uncommon. But a couple of sort of alternatives to this are the LAZ and ZLAS formats. Both of these try to do the same thing. LAZ is a format authored by Martin Eisenberg. Martin Eisenberg is the guy that writes LAS tools or LAS tools, which is a really commonly used Lidar programming suite, processing suite, I should say. Excellent bunch of tools. So he was kind of one of the first to make a play at compressing Lidar data. They're smaller, but like a lot of compressed data, they take more time to load and write. They're technically lossless, although Eisenberg and I would encourage you to think about what the actual resolution of your data is. Lidar data is rarely accurate beyond the millimeter level, so there's no point in writing out those extra decimals. So keep that in mind. LAZ is a relatively open standard. It's the most commonly used one after LAS, and it's becoming more common all the time. I'll show you some examples of this. So if you're kind of out in the wild looking for Lidar data, LAZ is increasingly likely to be what you're going to find. The big alternative to that is ZLAS, which is a compressed Lidar format developed by Esri. It's not an open standard, it's a proprietary standard. It's also sort of got there second. And so LAZ sort of snatched up a lot of the, think of it as market share of this data space. And because it's kind of a closed format, people have been a little bit resistant to commit to that. Governmental agencies in particular are not usually all that interested in locking themselves into a proprietary agreement with a company who then sort of holds the keys to their data. Most of them want to sort of adopt these open standards. And so as a result, LAZ tends to be a little bit more popular. Occasionally though, like for instance, the VGen data, a good portion of that is actually encoded as ZLAS. And their converters, both Eisenberg and Esri, have published converters that will convert between all of these formats. So once you're locked, you're really not locked in. It's just sort of a convenience thing. You can also store the stuff in a number of other formats. You can actually store LiDAR data in shapefiles if you want to. They're not very efficient, so I wouldn't recommend that. But you definitely can. You can actually write these things out as XYZ text files if you want to. This is not such an uncommon way to do it, again, because it's perfectly transparent, really easy to write. There's no special reader or writer required to do it, so why develop the idea would be why develop a special data container just for this data. It's just numbers. We record numbers all the time. So let's just use a standard number writer, whether that would be a pandas data frame or whether that would be an Excel file or whether that would be a text file. The reality is that the reason for this is that text is a very wasteful way of storing this kind of data, and Excel is just as proprietary as anything else. And they're actually, the way that the data is collected, they're actually sort of patterns of how it's collected that make it a good candidate for sort of a specialized format. Again, not necessary, I would say, but there are good reasons to use sort of point cloud specific binary formats. So where can you get the data? You can get it from the national map. This is quite easy to do if you just load up the kind of standard loader. You can look at the elevation source data for the area that you're looking at. Very few states, if you look at the availability of LiDAR point clouds specifically, have been scanned. So some exceptions to this: Iowa, North Carolina, Kansas, Pennsylvania. There are probably a couple of others that have come online. It looks like Arkansas is pretty close. Why these states? Minnesota is getting pretty close. Illinois, I think, is almost there. Why haven't more states done this? It's a little bit mysterious. From a person who uses LiDAR data all the time, the benefits of this technology are readily apparent. You can do so many different things with this kind of data. We'll talk about some of the applications of that in the future, but it kind of boils down to a cost and political issue. So most of the funding for this stuff often has to come from the counties themselves, although there are usually national and state programs that'll help kind of encourage people along. But oftentimes the county GIS offices have to take the lead in getting this in coordination with their state and national offices to try to do this. And some places are better equipped to do that than others. So if you have sort of a strong geospatial state leader, they'll often drive this. And if you don't, then you might lag. Areas that have a lot more people, you can see have been scanned. So areas kind of east-ish of the Mississippi, leftward maybe one state are often in better position to do this than others. But if you've got a relatively rural state or relatively rural county with a smaller tax base, it's hard to generate money for this stuff. And so it would be nice to see sort of some additional funding at the federal level to start scanning the Western United States, particularly. Again, the payoffs for these data sets can happen in very unpredictable and interesting ways. But it can be hard to sort of sell that to the powers that be. This is a zoomed in area on the national map showing you the data sources that are available, kind of zoomed in on the Virginia-ish area. You can see that the bulk of Virginia is still really not totally available. I will say, and we'll talk about this here in a second, the national map is not at all on the forefront of publishing the most recently scanned data. So more Virginia is actually available than what you see here. And that's why we want to talk about some of these secondary sources. But in this case, what I want you to see is that the file formats for the downloads at the national map level are given in LAS and LAZ. Again, the two most common ways of distributing LiDAR data. This is an example of downloading and taking a look at some of that data. So this is an area near my hometown in eastern Iowa. When you click on these things, you get a rendering of what that looks like. You can go back and look at the original metadata and how it was collected. Lots of good information here about that. And then you can download the LAZ. So this is redirecting you to an FTP site. And you can pull this stuff down and download it. You can see that I'm downloading it in LAZ format. And when I click on that file, we'll look at that in a second. We'll look at the visualization here in the next slide. Actually, we'll look at that here in not the next slide. Before we get into that, this is another way to download the data. This is the interagency elevation inventory run by NOAA. This is still active. I've often found this to be a better source for the most recent data. As we'll see, actually, the best source of the most recent data tends to be the state itself. But I found that nationally, you can see that the coverage of this actually looks quite a bit better and more complete than even the national map have. So if I'm the national map is my first stop, but my second stop is the interagency elevation inventory. This is an example of how to get that data. It's a couple more steps. So you can see here I'm downloading a zip file. Feel free to pause that and read what it says. What I'm doing here is I'm loading this data in here from a map server. And it's going to add a map of the coverage that's available. I can click on one of those polygons and I can get essentially a link back to the original data. In some cases, that's actually going to be the national map, and in some cases, that's going to be somewhere else. So you don't download data directly from the interagency elevation inventory. You just essentially get links back to the data, which is more efficient. You don't want to duplicate data distribution anyway. As I said, many states distribute LiDAR data via their own portals or web pages. This is an example of Illinois' portal. It requires a little bit of paying attention to sort of figure out where the stuff is. Once you kind of work within a state, you know, those data sources don't really change all that often. But you can see that there's a couple of counties still missing in Illinois. Those may have filled in by now, for all I know. I didn't update this slide this year. I think this is a last year view. But essentially, you know, you go to this web page, you click on data, you'll get a list of all of those different counties, and you can download both the data and examples of products associated with those as well. These are an example of some of the derivatives that you can get. So you can see individual counties here in Illinois. You get a single, usually, you know, for as many places have been scanned, most places have, if they've been scanned at all, they've only been scanned once. Some exceptions to that include when there are major storm events, NOAA often will take the lead in doing a coastal scan, so those can be quite useful. But other, to the point, other associated derivatives with these things include TINs, sort of surface reconstructions, and then under derivatives here, what you'd be downloading are DSMs and DTMs, surface models and terrain models. In the state of Virginia, the process looks like this. I'll usually just Google Lidar Virginia. That takes me to the VGen page. You can click that you want to get the Lidar data. And you can see the current map, which includes a good section of Blacksburg and Roanoke. But sort of surrounding that is sort of a sea of future deliverables. Some of these things have actually been delivered by now as well. When you click on a particular tile, you can see that in this case we're downloading a ZLAS file. So the Blacksburg data is all in this Esri proprietary format. That's not true statewide. It does vary a little bit. I would say most of the state is being delivered in ZLAS, but some of it isn't. So this is an example of kind of going through a web portal, which actually connects to an FTP server. If you look carefully, you'll see that FTP link coming up as you click, which is nice. It's kind of nice to have both the web portal and backed up by an FTP server to sort of simplify data distribution and attribution. So the link there, when you click on that, is an FTP link. Increasingly, one of my favorite sites to download LiDAR data is Open Topography. Open Topography is a user community, I think run out of San Diego. Essentially what they want to do is provide sort of a Wikipedia or OpenStreetMap-like public repository for point cloud data. People that sort of scan things on individual products and want to share those back out again to the community. So again, this is stuff that's sort of not state collected, but collected by individuals or organizations that still want to share their data back out again. For a lot of places, particularly in the Western United States where LiDAR surveys have not been widely done, this is an extremely valuable resource. This is probably your best third stop for LiDAR data. If you didn't find it on the national map and you didn't find it on the interagency elevation inventory, Open Inventory is your next best bet. Or sorry, Open Topography. Just recently, so this is February 19th, 2020, the USGS has partnered with Open Topography to distribute their data set that way. So now there's a portal on Open Topography that will let you access all of the data, I think stored on an AWS server. So fast download. It's a really good sort of partnership between the community, the government, and Amazon to distribute this data out to everybody. Another really nice visualization / distribution network is the USGS Entwine repository. Not everything is available here, but a lot of stuff is available here. This is a web page you can go to, usgs.entwine.io. It's browsable. It sort of reminds me of the SRTM tile grabber, a really super easy, no nonsense. I just need some LiDAR data, give it to me kind of a website. So I would encourage you to use this as well. This is an example of what using that system might look like. You can see actually that there's links to the data down below here. But you can just browse on a web map, and within the browser, you're essentially going to get to look at the data manipulate it. There's a whole host of options that you can use. You can recolor the data. In this case, I'm coloring it to an elevation value. Totally interactive. I can apply vertical exaggeration. I can change the color mapping a little bit here to bring out details in higher or lower elevation. Just a really powerful way to just, if all I want to do is get a quick look at the data, particularly for visualization purposes, it's hard to beat this. There's a number of different tools you can use. You can sort of draw bounding boxes and clip things. In this case, I'm looking at a profile tool. So you can draw profiles. They don't have to be straight lines. You can draw curvy lines. And then one of the things that you can do that's super useful, show it here in a second, is sort of looking at those things in profile and then opening up a 2D profile viewer to look at those things as well. So in this case, we'll just draw a single line here. There we go. And that sort of gives you a good look, but then there's another box that you can click here. There's me hunting around for it. Sometimes the user interface is not the best, but it's super powerful. Here it is. Click on the 2D profile button and you actually can render that profile directly from the point cloud. And not only that, but in the upper right hand corner of that 2D profile window, you can actually re-export that profile back out again. So it's interactive. There's a ton of sort of base tools to sort of work with this data. Entwine, here we're using sort of Entwine is a way of sort of storing and streaming the data. It's backed up here by what's called Poetry, which is a kind of a web project to visualize LiDAR data in the browser. We'll talk more about that in the future. But just a really great tandem of data plus visualization. There's a lot of different kinds of software out there to help you manage, manipulate, process, analyze LiDAR data. ArcGIS Pro can do it. It's an okay way to bring your data in. There's a lot of different processing that you can do. It's not really LiDAR specialized, although it's getting more LiDAR specialized all the time. It's miles better than it was just a couple of years ago. And I expect Esri is putting a lot of resources behind this, and I expect it's going to get better and better as the years go by. And we'll talk about some of that stuff in the technical side on the notebook. There's also TerraScan. So TerraScan is a proprietary software. Global Mapper is another one of these. There's really too many of these to list. My guess is that Global Mapper is probably a close second in terms of what I hear people using if they're using proprietary software. There's open source toolkits that will process and visualize LiDAR data too. LazTools is one of these. LazTools is actually technically not open source. It's sort of in a bit of a no man's land between the two. You can download the tools for free. You can use them if you're an institution, if you're a business. You should certainly license those things. But it's some of the tool set essentially is in the open source community, and much of it is not. But even so, it's very powerful. A lot of people that I know that are sort of working with LiDAR data use this tool set. I use it for processing, much less for visualization, but it's very effective on the processing side. The two tools that I use probably more often lately, one is Cloud Compare. So I'll show you Cloud Compare in some detail here in a second. It's a GUI interface, although there's some command line tools that are really powerful as well. It's a GUI interface that you can use to load your LiDAR data. You can calculate meshes, you can manipulate it, you can filter it. Lots and lots of different applications here. So I'll show you a little bit more about that in a second. Increasingly, I'm interested in the Point Data Abstraction Library, or PDAL, sometimes pronounced Poodle. It is a parallel project to GDAL, which is a sort of a geospatial library for taking apart, especially raster imagery. The vector part of that is now fused with that project. And so the kind of legs of PDAL and GDAL and OGR are essentially all of the best open source ways of dealing with your data. And so PDAL is much less useful for visualization, although there's some things it can do in that part. But it's particularly useful for all kinds of processing steps that can be sort of on the back end of a thing that handles the visualization. couple of other things worth mentioning. The point cloud library is another way of working with this data. I think it's sort of a little less geographic, which you might think, like, what other kind of LiDAR is there? Actually, increasingly, lots of things are being represented as point clouds. So lots of sort of handheld-based scanners for archaeological artifacts or teeth or a number of other sort of scanning rooms. It's not all geographic, and so increasingly point clouds are there's sort of specialized software for dealing with non-geographic point clouds. And then QGIS, the open source GIS software package, is also sometimes useful. There's some plugins for this that make that helpful, but I don't use it that much for that, and the reason is that some of the other toolkits I think are just a little bit better. So this is Cloud Compare. Cloud Compare is an open source software. It reads, it views, it manipulates point clouds. I use this all the time. You're going to be getting a chance to use this in the notebooks. It's specifically designed to handle point cloud data. That's less true for things like ArcGIS Pro, that's sort of dealing with lots of different kinds of data, images and vectors and whatnot. And so because Cloud Compare was sort of written from the ground up to handle millions and billions of points, it's just smoother and more efficient and easier to use for this kind of work than Arc Pro, and that's why I use it all the time. So this is an example of using Cloud Compare. So here I'm going to find a LAZ file to bring in here. Cloud Compare will not read ZLAS files, so you have to convert those if you want to use them. We're just dragging the data into the interface. There's kind of a standard open if you want, but you can just drag and drop. We've got a 9 million point record here, and this is from that area in eastern Iowa that we looked at a couple slides earlier. It looks funny when you drop it in here. What we're looking at here is scan rank, an attribute field that we probably don't care much about, but we're going to represent that as the Z value instead and use Z to map the color, and then the details pop out quite clearly. As you zoom in, you can again start to see sort of the point-based nature of this particular kind of data set. To add a little bit of depth, we can turn on what's called a shader. That shades sort of the stuff on the high angle with respect to the viewer. It starts to look a little bit more real. Very effective way of sort of looking at this. Tool I used all the time is sort of the scissors tool. You can snip out portions of a point cloud very easily. Just sort of draw a polygon and say I want to keep everything inside. It actually splits the point cloud into what was inside and what was outside, so you can just look at the inside if you want. We can move that around, and as we scroll down here to the options, we can change the color mapping. So the default is this kind of blue to red, but there are a number of different options out there if that doesn't do it for you. Green to yellow. What else? Here we're switching it back. We can change the bounds of the color map here, so we can add a little bit of higher contrast by setting the endpoints of our color map a little bit more inside the distribution of the data. There we've got a histogram, which lets us sort of visualize the data. And one other kind of fun one, we can actually visualize our data in true 3D with Cloud Compare. If you've got a pair of 3D glasses, you can use that to take a look at your data set. And that actually has plugins for full sort of shutter-based 3D glasses, as well as the Oculus Rift. So you can use your Oculus Rift to look at this data set. This data is going to play through one more time. If that wasn't totally clear, you'll get a chance to work with Cloud Compare in your notebooks. Definitely let me know if you have questions. Again, I use Cloud Compare almost daily, certainly a couple of times a week. Just a really fun and easy way of working with LiDAR data. With that, we will wrap things up. Thanks for listening. This again was the part one of a three-part series on LiDAR. So stay tuned for the rest. Thanks, and we will see you next time.